Assalamualaikum. As part of our VLSI technology sessional course, this project involves designing a simple CPU, the SAP-1, using Logisim regulation, with a key focus on implementing a control sequencer to enable automated operation. I am Saidur Rahman Amina, ID2008044, and I am excited to demonstrate the design and implementation process of this CPU in Logisim. To begin our exploration, I will first present the complete SAP-1 CPU architecture operating in both manual and automatic modes. Before transitioning to automated execution, it is essential to examine the key components required for manual implementation, detailing their roles and interconnections step by step. This foundational understanding highlights how each element contributes to the processor's core functionality. The general-purpose registers for A and B serve as temporary storage for operands, facilitating arithmetic and logic computations by holding intermediate data values during instruction processing. The arithmetic logic unit executes fundamental operations such as addition and subtraction, drawing inputs directly from registers A and B to produce results that can be stored or further manipulated. The program counter maintains the current memory address of the instruction being executed, automatically incrementing after each cycle to ensure sequential program flow. A 4x16 decoder interprets the 4-bit opcode portion of an instruction, generating one of 16 distinct control signals to specify the operations being performed. At the memory level, the SRAM cell represents the fundamental unit for bit-level storage, while the 16x8 SRAM forms the full memory array housing both program instructions and data operands for retrieval during executions. The instruction register captures the fetched instruction from memory, passing it into its opcode for control and operand for addressing component. A ring counter produces sequential timing signals T1 through T6 or beyond, synchronizing the micro-operations that comprise each instruction's execution phase. And the instruction decoder analyzes the opcode from the IR, enabling the appropriate control line for the specific instruction type. Finally, the control sequencer introduces timing signals with decoded instructions orchestrating the automated fetch decode execute cycle that drives the entire CPU, preparing the memory for program loading in manual mode. With this component in place, we now initialize the system for manual operations. To load the program into RAM, we activate the chip select pin by turning on the CS enable pin. And to load the program into the RAM, we have to switch the debug mode to on. And as for the safety, we have to toggle the PC reset so that the counter starts from 0 always. Now we will select the address for the SRAM that we want to store the data, and the first address is given 0, and now we have to select the address by turning on the MAR-in enable manual pin and then giving it a clock pulse, turning off the MAR-in enable manual pin. The first address is now selected, and now we have to give data that is load A13, and the binary value of the load A13 is 00011101. Now we have to turn on the SRAM light manual pin, giving it a clock pulse, turning off the SRAM light manual pin, and the data is stored in the address. Now we will have to select the next address during turning on the MAR-in enable manual pin, giving it a clock pulse, turning off the MAR-in enable manual pin. The address is selected. Now we have to give the data, binary data for load B14, that is 001011. 1 1 0. Now we have to turn on the assembly manual pin, giving it a clock pulse, turning off the assembly manual. And now we will select the next address and then turning on the mark enable manual pin, giving it a clock pulse. The address is not selected. Turning on the mark enable manual pin. We have to give the binary data of tag, that is 0 0 1 1 0 0 0 0. We have to turn on the assembly manual pin, giving the clock pulse, turning off the assembly manual pin. And now we have to select the next address. We have to turn on the marking enable manual pin, giving it a clock pulse, turning off the marking enable manual pin. Now we have to give the address for storage system, and the binary value of the storage system is 0 1 0 1 1 1 1 1. Now we have to turn on the assembly manual pin, giving the clock pulse, turning off the assembly manual pin. And now we have to select the next address, that is, and then we have to turn on the mining enable manual pin, giving it a clock pulse, turning off the mining enable manual pin. We have to give the binary value of false, that is 1 1 1 1 0 0 0 0. We have to turn on the assembly manual pin, enabling the clock pulse. Now turning off the assembly manual pin. So all the instructions have been loaded, and now we have to load the data that we want to store in register A and B in the memory address 13 and 14. So we have to give the address 13, turning on the marking enable manual pin, giving it a clock pulse, turning off the marking enable manual pin. Now we have to select the binary value of 44, that is 0 0 1 0 1 1 0 0. Now we have to turn on the assembly manual, giving it a clock pulse, turning off the assembly manual. Now we have to select the 14 address, turning on the marking enable manual pin, giving it a clock pulse, turning off the marking enable manual pin. And now the binary value of 25 is 0 0 0 1 1 0 0 1. Turning on the SRAM right manual pin, giving it a clock pulse, turning off the SRAM right manual pin. As the SRAM is loaded with all the data we want to store for the operation next, so now we will turn off the debug pin. And now again we have to give the PC reset again, so that the counter gets counted from the 0 again. Now this sample program comprises 5 instructions, each spanning 6 T steps requiring approximately 30 clock cycles in total. Each set of 6 pulses completes one full instruction cycle, allowing us to observe the processor's behavior dynamically. So at first, if we give for the first 6 clock pulse, the data will get stored in the register A. So we are giving 6 clock pulses. We can see that the binary value of 44 is getting saved in the register A. So for the next 6 clock pulses, the binary value of 25 will get stored in register B. So we are going to give next 6 clock pulses. We can see the binary value of 25 that is showing in the register B. Now for the next 6 clock pulses, the add instruction will get executed and the result will show in the register A. As you can see that the result is getting stored in the register A. And for the next instruction, we want to store the result into the 15th memory address. So now for the next 6 clock pulses, we will see the operation being executed. As you can see, the address has been stored the binary value of 69 in the 15th memory address. So now we will give additional 3 clock pulses for halt, and now the final cycle encountering halt, halting the processors and concluding the program. Through this process, the control sequencer seamlessly manages the fetch, decode, execute loop powered by synchronized clock pulses. By monitoring registers, memory, and control lines, we gain invaluable insights into the SAP-1 step-by-step orchestration, demonstrating the materialness of hardware control in a simple yet functional CPU design. So now we are moving to the automatic mode. In automatic mode, instructions are loaded autonomously, leveraging specialized components to streamline the process. This includes a program counter, with an integrated loader and instruction loader to transfer code from ROM to RAM, and an enhanced instruction and the enhanced instruction decoder that supports the jump instruction. The control sequencer is also updated to incorporate logic for handling jump operations, ensuring seamless execution of complex instruction flows. To facilitate this, I developed an assembler that converts SAP-1 assembly code into hexadecimal format. The resulting hex file, as outlined in the program table, is uploaded in the ROM by editing its content. To transfer this instruction and data to RAM, we activate the debug mode, reset the program count to 0, and apply clock pulses. So each of the 16 RAM locations requires 2 pulses, one to set the address and another to write the data, totaling 32 pulses. Upon completion, the RAM is fully populated with the program and data are ready for execution. So now we will give 32 clock pulses for the SRAM to be fully loaded. As we can see, the RAM is now totally loaded with data. So now we are going to turn off the debug pin, again turning on the TCL6 pin and turning off it, so that the counter value returns to 0. And now we will give the clock pulses to execute the operation, so like as the manual mode, like storing the data in, loading the data in register A, loading the data in register B, and then adding them. And also we have updated the code from manual to automatic, and that is we have added jump in here. So first we will give 6 clock pulses to see that the register A gets loaded with the data, binary data of 44. As you can see, the register A is getting loaded with the data, binary data, and also the hex data of decimal data 44. And now for the next 6 clock pulses, we will see the change in register B. As you can see, the register B is getting loaded with the hex data of decimal data 25, that is 19, and also with the binary data is showing here of the decimal data 25. And now we will see how our jump works, that our counter value will jump to 25 for the next clock pulses. As you can see, the counter value has jumped from 2 to 5 as we have added jump here, and now we will see that the add instruction will work in register A, and the value of register A will get changed with the result of register A plus register B. As you can see, the register A is getting updated with the value of register A plus B, that is 44 plus 25 and decimal 69, and the hex value of decimal 69 is 45. So now we will store the data in the 15th memory address. So we have to give another 6 clock pulses. As we can see, the data is getting stored in the 15th memory address. So our executions have been completed. To terminate the process, we have to give additional 3 clock pulses to halt the program. And now the program is halted. This automated process showcases the SAP-1's ability to execute a complete fetch, decode, execute cycle, efficiently managing both arithmetic operations and control flow instructions like jump through the enhanced control sequencer. Thank you.